All right, welcome to ABE 121. This is Agricultural and Biosystems Structures Engineering, and we are in week 3 of the class where we're going to talk about the beam, a significant structure in carrying the loads of buildings and structures. Now, uh, we will be dealing with uh, here in this discussion just the wood and the uh, concrete type of beams because we're going to talk in detail uh, the steel in the laboratory, and also that the steel has been already discussed in your in the strength of materials prerequisite subject of this course. Okay, particularly in the I beams. Okay, solutions to that are have been discussed in strength of materials or materials of, I think that's in materials of materials of engineering. Sorry, it really is strength of materials. All right, so or the mechanics of materials, sorry, but not materials of engineering. So let's proceed with the discussion on the beam. Okay, and we want this part of the structure to avoid failure. That's why we're going to consider in the design the bending, horizontal shear, and the bearing stresses. Now, these stresses are considered because uh, this could be the modes, or one of this could be the mode of failure of the beam, and eventually the structure. That's why we are going to talk about this in particular. Now, the bending stress of a rectangular wood beam would be shown. It's sigma B equals M over S. And we have a allowable bending stress that is specific to the material. Now, M is based on the bending moment, which is or computed or determined using the shear and moment diagrams that are also uh, already discussed in the mechanics of materials course prior to this subject. Now, similarly, we have the horizontal shear as such. Okay, it's in the shear and bending moment diagrams that these are determined. So this is based on, or the bending moment is based on the diagram. The maximum would be determined in uh, such way. That's why it is an important, okay, uh, factor to master the shear and moment, or bending shear and bending moment diagrams of beams. Okay, for the horizontal shear stress, this is a derived equation. This is 3V, or the formula is for sigma V is 3V over 2A, and we have again the V as the design shear. So this is the point of the highest shear in the shear diagram. Okay, now the area is simply the cross-sectional area of the rectangular wood beam, and we have a maximum horizontal shearing stress that is uh, well determined by the type of material, or the timber that is being used as the wood beam. For the bearing stress, okay, we have the actual bearing stress, okay, designated by the sigma, okay, and a perpendicular representation. And it simply is the reaction force, okay, in that in the position and over a certain area of the beam. And the area would be, well, the contact area or bearing area between that beam and a support. Well, the beam is supported by columns, and the beam itself could support another column or a another piece of the structure in a building. Okay. Again, there's a allowable design bearing stress. Okay, that is uh, uh, specific to a material, okay, to the wood or the timber material that is being used, and it's uh, well, since it's specific to a material, uh, it should be emphasized here that there is a variability to the compressive stress of the wood beam, and for here, it's the compressive stress perpendicular to the grains. We have the grains, okay, along the direction of the position of the beam. That's why we have a bearing stress that is perpendicular to the grains. Okay, so another consideration in the design of beams or wood beams would be the deflection, and it's simply the deformation that accompanies the bending. Okay, let me also go back to the uh, bearing stress. Okay, let me share a diagram. Okay, uh, let me just go back. Okay, I have to connect. Uh, let me just connect. All right, so I'm now connected. Okay, as we can see, we have here a diagram of a beam with a column support at the bottom, its edge, and another column above it. And just to represent or show to you what happens with the this beam is that we have a contact surface between the column over here, so that there's a reaction force, due to the weight of the column, okay, and it's going to be this P, and that reaction force on the beam would be distributed, okay, at its at point of or area of contact between the column. That is now representative of the bearing stress, okay. Similarly, we have a bearing stress here between this beam support and the beam itself. But in this kind of uh, diagram, or in this kind of situation, the beam would be having a bearing stress opposite to the direction of the one uh, between the column and the beam. So this is a very basic concept in the mechanics of materials, and very much um, usable in the analysis of wood beams. Okay, and also similarly to with whatever material uh, can be used as the beam. Okay, let's go back to my presentation. Uh, we have now the deflection, right? Now, uh, we have here a beam, okay? We have here a beam that's uh, located or supported in its ends by uh, okay, you have here a beam supported in its ends, okay, and so we have a reaction force here, a reaction force here. Now the tendency for this beam is to, well, sag, okay, in a way like this, Okay, so we have here a uh, distance that is called the deflection of the the beam. Okay, and we have an allowable uh, design limit, okay, for the beam deflection, and this is um, important in that we we avoid such deflections because ultimately it would lead to the failure of the beam. For simply loaded beams, such as this one, we have the maximum deflection at the center span. Okay. Now we have deflections for various cases, such as for uniformly distributed load. We have also for concentrated loads, and then we have specific to structural members. Now, for the deflection, okay, we have of uniformly distributed loads. This is a derived equation, and uh, what can be done is just, or what should be done is just to input the values of the load, okay, the length of the span of the beam, and the modulus of elasticity and the moment inertia of the beam section. The modulus of elasticity is again specific or particular to the timber to be used, and it's in Newton per m squared. And we have the moment of inertia, okay, the moment of inertia of the beam section based on the uh, cross-sectional area. For I beams, okay, it's very much computable. Okay, for the equations are already given, and it has been already discussed previously in the mechanics of appearance. And I won't be going through that anymore. Okay. So the equation is has been derived, and it's 5 over 384 WL over E over I. We have the L, or that the span raised to the fourth, raised to the 4. For concentrated loads, okay, we have 1 over 48 PL over EI, with P as the concentrated load of the beam. We have again, the ENI as the modulus and the moment of inertia specific, specifically or particularly. Okay. So the beams are carrying a single concentrated load at the center span for this case. Okay. Let's go back. So we have a force here. Okay, if that's the case, okay, we have a force the center of the beam, okay, just over here. All right, for um, concentrated loads, okay, we have 2 equal concentrated loads at the third points of the span length. This is 23 over 648. Okay. Now, again, this is our derived, but in any case, these are very much computable using the uh, shear moment diagrams, okay, and um, the modulus of elasticity of material. Okay, for structural members, okay, particularly roof member supporting plaster or floor member, we have the maximum allowable as for those with live loads only. Okay, it's L over 360, while if there are dead loads, okay, we have L over 240. Okay. Now for reinforced concrete beams, since these are uh, a com composite material, okay, that's made up of concrete and reinforcing steel bars, we have to consider also a separate concern here on the design considerations, which is on achieving a balanced design. And this is important because uh, in concrete beams are expected to be carrying more or heavier loads than wood beams. And the very situation here is that we do not want to have an over reinforced design, because if that's the case, uh, when the beam reaches the ultimate load, okay, failure can happen without any warning. So it's either we go after the balanced design, but that is a point or a critical value, which is just a little less than the overall enforced design. Now we then have to master solving for an under reinforced design, so that okay, the steel reinforcement will reach the limit stress before the concrete does. And in that way, okay, we are able to see the concrete cracking, because the steel is already overstressed, and the concrete remains under stress. Now, the the steel will be introducing that stress into the concrete. That's why cracks appear. And in such a way, this is a good indicator that the uh, building is still being supported, okay, by the steel and the concrete, by whatever is remaining in there. Now, it avoids accidents because the failure, okay, is uh, can be addressed, okay, by improving on the design, by improving on or remedying the cracks. And unlike when it's over reinforced, the failure just happens suddenly. Now, in the design of reinforced concrete beams, we consider this diagram. Okay, we consider this diagram, and let me just move over uh, before we proceed with this one. I want to tackle in detail uh, the I want to tackle in detail the all right, I'm already presenting. I think that's it. All right, so I'm already again back to my other screen, and we have here, all right, a cross section of the beam I've already shown a while ago that's been uh, um, specified with the uh, dimensions and the um, configurations of the solution to a uh, design of a reinforced concrete beam. Now, what I want to emphasize here is, again, we are looking at the cross section, but in the isometric, okay, we have something like this, a beam. Oh, yeah, I think I'm just going to draw the oblique. So we have a beam that looks like this, and we have the structural reinforcing bars over here. Now, it's such design because, as you can see, the beam would be supporting from above. Okay, the force is going down, and with that, the beam would be experiencing compression. Okay, this is the deformed uh, beam. Let's try to use a different color. represent that, right? We just use this one. So this is going to bend, and the upper portion will be experiencing compression, and while this one would be experiencing tension. And as I have already shown in the diagram, that's why we have the forces already as shown in the diagram, because it's represented by this uh, forces C and T. Okay, these are the forces C and T. That one I've already shown. Okay, in the diagram in the other screen. Now the dimensions important in this design are BH. Okay, remember in the computation of the um, modules of, oh no, the moment of inertia, the radius of, sorry, yeah, the moment of inertia. We have here the P and H as important parameters. Okay, now it it's very much the same in here. We have the width. B is the width of the concrete. Okay, and H is the height. We have here a dimension D that is representative of the distance of the reinforced concrete to the top portion of the beam. And KD is the compression zone. And so this is from the centroid. Okay. Oh, no, not centroid. This is the uh not the uh or this is the center, okay, centroid of um the whole cross section. Now KD, okay, this is the height of compression stress zone, or this is percent. This is the percent of the T, okay, uh where there is neither compression nor tension. And so for this one, we have also other defined dimensions. We have the FC, okay, the force of compression over here. We have the force of uh, the tensile stress, okay, in the steel bars over here. F, it's Fs over N, okay, and we have Kd over 3 over here. And we have another JD, which is the intermoment arm between T and C. Okay. Now, what are these dimensions important for? You want to solve for the uh, allowable stresses, okay, or the dimensions that we want, so that we can cover for those uh, stresses that are to be supported, or the loads that are supported causing the stresses. Now, uh, for the design of the concrete beams, we have the following formulae, and it involves, for example, the percentage of reinforcing, which is simply the cross-sectional area over the BD. This is the AS is the cross-sectional area of the reinforcing steel bars, and we have M here. Okay, we were talking about the JD as the internal moment arm between T and C. So M is equal to uh, CJD as much as TJD. But we are going to arrive at different formulae so that we can solve for the FC, okay, and the FS separately using the different equations. We have again the same bending moment. Okay. Now the AS, we can also solve using the moment. Okay. All right. So we were talking about the balance design, and to arrive at a good number, uh, of an under-designed beam, we can limit that to 0.75. And this is uh, to ensure that we are very far from the over designed beam. And we have here the values of the K, J, and the P for balanced design. Okay, these are the guiding uh, uh, num numbers into the computation of uh, the allowable forces, okay, of the final beam design. All right. So we were talking about the with beams this time, and next meeting we're going to talk about the column. Okay. Thank you for listening, and I'll see you next time.